according to the schedule, it is time to start, and I'm happy to announce our first speaker, Sergey Filippov, with the talk Superior Resilience of Non-Gaussian Entanglement in Local Gaussian Semigroup Quantum Dynamics. You have 25 minutes plus 5 minutes for questions. You're welcome.
Thank you very much. It's my pleasure to participate for the third time in the series of conferences, OPSO. I really enjoy every event organized each year. So today I would like to talk about some semigroup dynamics, which is Gaussian, and to reveal some unexpected phenomena, namely that optimization problem involving Gaussian channels actually has a solution in the set of non-Gaussian states. So in the paper that is cited here, we have kind of a freedom to say that we shake the Gaussian world paradigm in this scenario. So, but later Mark Wilder wrote to me and actually showed that there were some papers where people already studied optimization problems for Gaussian channels where the solution is obtained at a non-Gaussian state, but they are also quite recent papers. So I think that this kind of exploration started in 2020s. So let's come to the subject of the presentation. So entanglement is a phenomenon of quantum correlations, and those correlations are known to be quite fragile with respect to noises in the communication lines. But it's also a kind of useful resource, and the presence of entanglement is highly desired in quantum algorithms. So say we have Alice and Bob located in different laboratories, and the entanglement source, which is and the goal is to distribute that entanglement between Alice and Bob. And having this entanglement as a resource, they can perform various tasks, starting from teleportation of quantum states and superdense coding and so on. So the idea is to share entanglement between Alice and Bob. But when we send those signals encoded, say, in electromagnetic field radiation, we send it through some physical systems, physical channels. And these physical channels are noisy ones. So, and that noise corrupts the states and corrupts entanglement. And one of the main physical descriptions of that corruption is loss of information. So just photons that we send can be simply lost in those communication lines. So how do we usually fight with losses? We use amplifiers. But as I will briefly remind you, amplifiers also introduce noise. So both lossy channels and amplifier channels, they introduce noise to the signal, and that noise spoils entanglement, and after some threshold value, the state becomes disentangled. And it means that it's no longer useful for the tasks I mentioned before. So in this talk, we deal with Gaussian states. So it means that we encode quantum information not in the polarization degrees of freedom of photons, but into the amplitude of electromagnetic field. And mathematically, this can be described in terms of characteristic functions. So here we have a Weyl operator, which is a generalization of the displacement operator in quantum optics. So it's given by this exponent, where Q and P are canonical position and momentum operators for corresponding modes. X and Y constitute the Z vector. So number of modes is n. In our today's talk, n will be equal to 2. So canonical commutation relation should be respected, of course. And yeah, this is how we describe the characteristic function in terms of real variables x and y. And the attenuation, so loss of the signal, and amplification can be both described within one formula, and it shows how the characteristic function at the output is related with the characteristic function at the input. So argument of the input is multiplied by some matrix K, and extra exponent is added. So K, in the case of phase insensitive amplification and attenuation, is simply proportional to the identity matrix. This is a formula for one mode. And M is also proportional to the identity matrix. So K is actually this kappa, sorry. Kappa is actually the gain factor. So in case of attenuation, it is between 0 and 1. In case of amplification, it is larger than 1. And if we simply add classical noise, then kappa equals to 1, but mu can be larger than 0. And fair physical channels, so those that are completely positive and rest-preserving, necessarily satisfy the relation here. So the noise parameter mu cannot be smaller than this value. And characterization of all possible Gaussian one-mode channels is given by Holevar. And here we consider only the typical phase-insensitive examples of attenuation and amplification. So quantum limited noise is exactly the smallest noise value we can achieve. And what is above that lowest value is called extra noise. So of course, the conference is devoted to semigroups. So I should present the equation and the corresponding semigroup description of that physics. So I just copied an equation from the Breuer and Petruccioni book. So the dynamics of the density operator would be given by such an equation. So you see here A is a photon annihilation operator, A dagger is photon creation operator. So you can easily recognize Lindblad terms here. So there are two contributions. One of them with a factor gamma 0 n plus 1, where n is the average number of thermal photons in the environment. So the dynamics given by that equation is actually within the class I have just described here. And kappa and mu are expressed through parameter gamma in the following term. So gamma combines those gamma 0 and n average is now here. So this semigroup dynamics is within the class of channels that I described, and each particular channel can be considered as a snapshot. So this is a snapshot in the dynamics. So for some particular time moment, we will have the dynamics described by that. And here is a picture which actually shows how the noise parameter mu and attenuation amplification parameter kappa change in time in that semigroup dynamics. So we start from the point where kappa equals 1. It means there is no amplification, no attenuation, and noise parameter mu equals 0. And then when time goes on, in case of attenuation, we have a decrease of kappa and increase of mu. And in the noise limited, quantum limited, in the quantum limited operation, we achieve noise parameter mu equal to 0.5. And it simply means that we replaced our signal by the vacuum field. So this line from the point 1, 0 to point 0, 0.5, it's actually a line where the signal is continuously attenuated up to the point where the vacuum is at the output of the channel. Of course, we can consider the situation where the more noise is added, so more and more noise is added. In case of amplification, we go in the right direction. So kappa increases, so there is an increase in intensity of the field, but the noise also increases. So this is a relation. And now you can wonder what is this blue line denoted by EB. This is so-called entanglement breaking region. So if our dynamics is now above that blue line, it means that the noise is so strong that all possible entanglement between one mode and the other mode where the channel X is destroyed. So here is a pictorial representation of what I have just explained. So imagine that one part is not affected by noise at all. So this is a straight line on top. And the other part is affected by the channel. So if parameters kappa and mu such that the corresponding point is above the blue line, it means that any entanglement will be destroyed by that channel. But you see that this physics, also studied by many authors in 2000s, it describes only one-sided noise, where the noise acts on one part, one mode of the field, and the other mode is not affected by noise at all. So the question that was interesting to researchers was what would happen if the noise acts on both parts of the signal, because it's more related to practice. So, and the case of symmetric noise was considered in several publications. One of them is by Sabapathy, Ivan, Simon in 2011. And the other is my publication with Mario Zeman in 2014. So where we studied that symmetric case. In the case of symmetric noise, we show that Gaussian states could remain entangled below the red line on the upper figure. So you see there is a light green triangle below that red curve. And it's actually easy to derive this bound via the Simon's criterion. So in 2000, Simon derived a criterion for Gaussian states to be entangled or to be disentangled. So it's if and only if criterion. And it's easy to use that to derive that red line. What was non-trivial and what Sabapathy, Ivan, and Simon did, they found that in case of that symmetric attenuation or amplification, those dots, black ones and white ones, they correspond to the preservation of entanglement for some specific state. In our paper with Mario Zeman, we actually improved that bound and showed that for every parameter kappa and mu below the red curve on the bottom figure, we can preserve entanglement. And you see that this red curve on the bottom figure is, so it defines the region which is strictly larger than the region on the upper panel. So it means that the non-Gaussian states remain entangled longer than any Gaussian state. So specific non-Gaussian states could could outperform all Gaussian ones. But this was in the case of symmetric noise. And the loophole was that in case of asymmetric noise, so when the noise acting on one side and the noise acting on the other side, so they are different. Actually, two parameters kappa and mu could be different. So in this case, there was a loophole that the Gaussian states can be better than the non-Gaussian ones. And what we did in our recent paper, we closed this loophole. We showed that there exist some specific non-Gaussian states that depend on those parameters kappa 1, 2 and the mu 1, 2, such that they remain entangled longer than any non-Gaussian state. And the corresponding area of parameters where we were able to prove that superior resilience is given by this inequality shown at the bottom of the slide. And this inequality, so we rigorously derived it, and this inequality defines a strictly larger figure as compared to that for Gaussian states. So we proved that non-Gaussian states can remain entangled where no one Gaussian states can. And actually, the referee pointed out the paper by OPSO, published in 2011. And that paper had a very opposite title. So the title was Simple Proof of the Robustness of Gaussian Entanglement in Bosonic Noisy Channels. So in that paper, the claim was that Gaussian states provide, so if we want to preserve entanglement in that semigroup dynamics I showed, so there will be a solution in the class of Gaussian states, which remains entangled the longest time. And this is opposite to what I claim here at this talk. So in the paper, we analyzed arguments of that paper and showed the drawback, where the line of reasoning was actually not correct. So here I simply show that a paragraph from our paper where we somehow argue with the statements of OPSO. So and show that in our opinion they were incorrect. And actually what was previously derived in the case of symmetric noise by Sabapathy and us back in 2014 is also in favor of our approach and in contrast to OPSO's statement. All right, but I will not focus much on this. So if there are questions regarding that, I could explain what was wrong in that discussion by others. Okay, so the machinery we use to prove our main result is entanglement witness machinery. So the entanglement witness operator is given by the upper formula here, and it depends on the parameter lambda. So lambda is a real parameter which is greater than 0, and you can easily recognize that this kernel exponent, it gives as a result the operator W lambda, which is unbounded. So the operator W lambda is unbounded, but when we take trace of that operator with some density operator, we can still get finite value. So it's not a problem. And why is it called entanglement witness? It's called entanglement witness because when we take trace with every factorized state, so every state of the form phi, chi, chi, here at the bottom, at the second line, so we get non-negative value. Indeed, we have some integral squared, absolute value squared, and this is non-negative always. So if now I take, okay, let me check if I can write. So if I can take some state and yeah. So if I can take some state rho and take trace of that rho with W lambda, and I get value which is less than 0, it would be a direct indication that the state rho is entangled. So it is not separable. So this is what we use in our paper, is entangled. And of course, the values that we obtain here should be finite, so that parameter lambda cannot be arbitrary. It should be within some corridor. We define it in the paper. So the state rho that we deal with is actually obtained by acting of that semigroup dynamics, and the snapshot of it is phi kappa 1 mu 1 tensor phi kappa 2 mu 2 acting on some state psi c, which is written a little bit below. So in that state psi c is defined by another parameter c, and gamma is a coherent state, 0 is a vacuum state. So you see that it is a superposition of coherent states, of two-mode coherent states. And in the derivation, we actually consider the limit when gamma tends to 0. And when gamma tends to 0, we obtain the state which is written at the bottom of the slide. And here, 1 stands for the one photon Fock state. So that state psi c is actually one photon, 2-mode state. But the parameter c is chosen in such a way that to adjust to a particular choice of parameters kappa and mu. So let's see how the situation looks like. Oop, now I should erase everything what I wrote. Just a moment. Okay. Sorry for the delay. So this is a formal proposition. I will not focus much on that. It is just a claim that the output state remains entangled if the parameters are within the specific regions. I will better show the physics. So here the parameters A on horizontal and vertical axis, they correspond to the extra noise that is present in the one mode and then the second mode. And for example, if we choose a specific parameter C in the formula here, then we get a particular state, and these blue regions, they show where we have negativity of the entanglement witness average value. And you see that this is a kind of peculiar shape form which changes while we change parameter C. So while we change parameter C, the angle of that shape, of that figure, goes along the arc. And that arc actually defines the inequalities I showed here at the bottom of the slide, defines these inequalities. And you see that when we go along that arc, we cover all that region, and that region is strictly larger than that straight line, dashed straight line, and that dashed straight line, it is the boundary for Gaussian states obtained via the Simon criteria. So here I just give a visualization of that proof that we obtained with my former master student, Alena Tsemanova. And this is a plot which shows how the entanglement behaves in time in that semigroup dynamics. So green and blue lines correspond to the Gaussian entangled states, 2-mode squeezed vacuum. And yeah, there is a specific measure of entanglement in this case. It is on the left vertical line. So we see that that entanglement ceases, actually vanishes after some dimensionless time, around 0.35 in that example. But non-Gaussian states, which I showed you for some specific parameter C, they can remain entangled longer time. And these are orange and violet lines. And for them, we also have a kind of non-Gaussian threshold given by our inequality here. So the open question which remains is whether all states become separable if we violate this latter inequality. If this is the case, then we would prove entanglement annihilation phenomenon. But so far, we can only claim that non-Gaussian states have more resilient entanglement as compared to Gaussian ones. All right, let me come to the summary. So I briefly described attenuation and amplification in terms of characteristic functions and related semigroups. So there are some limitations on noise intensities that destroy entanglement of Gaussian states, and we showed that for non-Gaussian states we can tolerate larger noise. And the low intensity non-Gaussian states remain entangled within a wide range of noises beyond quantum limited performance for any degree of attenuation or gain. Thank you for listening.
Thank you. Questions, please?
Yes, I have a question. At first, thank you for very interesting talk. Did you introduce this witness, entanglement witness you used?
Yeah, the concept is old, of course, but the operator here, W lambda, yeah, we introduced it in 2014 in this paper with Zeman.
Mm-hmm.
And we used it, yes, we used it for symmetric case, but it turned out to be quite productive also in that non-symmetric case.
And also about you told us constantly longer than. Do you have some estimations of time following to the Gorini-Kosakovsky-Sudarshan semigroup?
Yeah, surely we are mathematicians, so we work with dimensionless parameters, right? So, and so here, say gamma times t, it is a dimensionless parameter. And this is the dimensionless parameter that I plot in the figures. So here, for example. So you can imagine that experimental physicists created a line with a very small loss. So it is almost perfect. In this case, gamma would be small. So that attenuation rate. So in this case, the actual physical time measured in seconds would be large. On the other hand, if we have a kind of a very lossy channel or very noisy situation, then that gamma would be large, and in this case, physical seconds would be small. So I don't know if I got your question correctly or not.
Yes, exactly. This is the case. Thank you very much.
Thank you.
More questions, please?
Well, may I ask a question?
Please.
Also, thank you for very interesting talk. I have a following question. Is it possible somehow interpret this phenomenon as spontaneous symmetry breaking, meaning trying to identify some symmetry transforming Gaussians to the Gaussians, which preserves this Gaussians before threshold, and after it would be an orbit between your states by this transformation. Is it possible to do something like that?
It's an interesting direction of research, but I'm not sure that I could answer deeper to that question. So in my understanding, the situation is the following. So when we had, say, symmetric losses, the state that remained entangled for a longer time, they were also symmetric. So we constructed them this way. So when we introduced some asymmetry, the states that we deal with also have that asymmetry. So this C parameter, it adjusts in accordance with those kappa and mu parameters. So somehow that C parameter depends on that asymmetry. But yeah, your question is interesting, but I don't know how to interpret that as symmetry breaking.
I mean, I think Gaussianity is a symmetry is by itself, because symmetry by something, symmetry under some Gaussian maps itself, because they map Gaussian Gaussians. So possibly there are some Gaussians which maps these Gaussians before threshold to the Gaussians, and after this will transform your states to some orbits of states which are not so simple, but much larger. It's the Gaussian transformation of these states you found. Possibly they are interesting too. I mean, possibly if it's possible to do something like that.
I don't know. Yeah, it's very interesting to explore it further.
Okay, thank you. Thank you.
Thank you for the idea.
More questions? Then let us thank the speaker again.